options of here right now, right? And you will be. I think I am very fortunate enough that I am telling you this thing, that there is a HVDC interconnector link between Ethiopia and Kenya. There is an HVDC link that is made by Siemens, and the training of both Kenyan engineers who are operating the station and Ethiopian engineers who are operating the station is being given by PowerGrid. Last year in the month of October, a delegation of around 20 engineers came to India, Ethiopian engineers. In first part, we have given them the hands-on training on HVDC, operation and maintenance, and how to run the system. And their second batch is coming in February of 20 engineers. Fine. So what is the need for this HVDC link? So whenever you have two countries, different countries, the two countries have different frequencies. Fine. So to connect these two countries, the AC line will always be a problem. It's not easy to connect them, first of all, and second of all, it's technically not feasible to connect two different frequencies via AC line. So, but whenever there is a transmission of electricity from one country to another country having two different frequencies, then HVDC interconnections are always used. Therefore, between Ethiopia and Kenya, Ethiopia is a hydropower generating country which has a lot of hydro reserves. So they are transmitting their power, excess power, to Kenya via this HVDC link. So whenever you have two different frequencies, the transmission of electricity happens over HVDC. So there is no AC link between these two countries. So asynchronous connection between two different frequency and voltages that can work because of HVDC. Then power flow control. You all know this thing, that in AC station, whenever there is a power transmission happen between the two stations, between the two nodes, then you do not control the power. How much power is flowing on the line will depend upon the load angle. You do not control the power, right? Depending upon the load angle, or in the layman language we call demand, the power will flow from one way to another or from this way to another. The power can take any other way. You do not have any control over it. But in HVDC, you have full control of power. You can define how much power going from X to Y or Y to X. Like in Ethiopia and Kenya link, they define that 500 megawatts of power will flow from Ethiopia to Kenya. Let's say today. And tomorrow they decide, I change it. Let's say 500 megawatt will flow from Kenya to Ethiopia. So this direction of power from one point to another and the magnitude of power, how much power it will flow, this can be controlled by HVDC. This is the major factor of HVDC or major plus point of HVDC. This type of control you do not have on AC networks, on AC lines, right? Then there is an added benefit of stability and power quality. What I mean to say stability, let's suppose if two countries having different frequencies, if they are linked with each other over AC transmission line, fine, then what will happen? Disturbances in one of the region will cause tripping in the another region. This is called cascade trippings. Then disturbance in one of the region, they travel along the network. But in HVDC systems, this does not happen. If the two countries are connected by HVDC network, then disturbance of this network will not travel over the HVDC link. The DC link does not carry those disturbances. So the other end will remain stable. So this stability is a very important factor in case of HVDC. Right? Then there is environmental advantage. What does that I mean by environmental advantage? We have a slide for it also. If you look at the tower of HVDC, then the tower of HVDC require very less right of the way. They are very compact in nature as compared to AC towers. Fine. When you have a less right of the way, you understand what is right of the way?
Yes.
When the line passes, then you have to make the foundation of the tower. So in that case, right of the way for HVDC transmission is less as compared to AC transmission. Then line losses are less because there is no frequency in a DC network, so there is no corona losses. Corona losses are directly proportional to frequency. Frequency, there is no frequency, no corona losses. Then there is no charging current also, because charging current is a phenomena associated with AC current. Depending on DC flows on the line, there is nothing called charging current. Plus, there are only two conductors in the HVDC network, plus and minus, and your I square losses are directly proportional to resistance, right? So in AC you have R, Y, B, three phases, three conductor, three resistances. In DC you have what? Two conductors, positive conductor, negative conductor. That's it. So I square losses are also less. So the loss of energy due to the transmission is less. So this is actually why HVDCs are required all over the world. Right now also you have heard about the this advancement or the shift of energy scenario in the world. Like everybody in the world is talking about green energy, right? We are trying to move away from thermal fossil fuels, and also we are not very much reliable or do not want to be very much reliable on nuclear power because of the recent unfortunate incidents which had happened in Japan in Fukushima reactor. Because of that, we are not interested in nuclear power also. So the only way we can sustain our world and we can every country should sustain its energy needs is via renewable energy. And there are only two options for renewable energy. One is solar and the other is wind. Fine. So this transition of the world from solar, from fossil fuels to renewable energy is causing a lot of impact on HVDC, because in Europe where you have big wind farms, they are going for wind farms. There is only one possibility to tap the power from the wind farms or solar parks to the main grid is via HVDC. So there are a lot of HVDC interconnections are coming up in the world, especially first in Europe, then in United States, and then will come in India and other SAARC countries. So we are now HVDC has become more and more prominent in nature. You will find a lot of HVDC coming up in the near future. Now HVDC is a special technology where you can have different modes in which you can operate it. Do you have any idea about how many modes you can operate an HVDC link? No? Then we talk about the different modes. Because in AC these things doesn't exist. In AC you just switch on the breaker, that's it, and the power will flow depending upon the load angle, power demand and supply, and you do not have to do anything. But in HVDC a lot of complicated things happens. You operator can control the power in magnitude also and in direction also. Plus there are different modes in which you can operate an HVDC station. This is a typical HVDC station. Fine. And it shows its components. What are these? This is your AC bus, right? HVDC systems consist of two stations first of all. They are point-to-point connections. This is one station. Let's suppose in your term, I can give you an example of your two neighboring countries, Ethiopia and Kenya. This is Ethiopia side. This bus belongs to Ethiopia, right? At this 400 kV bus of Ethiopia, they have connected two converter transformers. Fine. Then these are valves, thyristors valves. The main purpose of these two is to convert AC into DC. AC current is coming from here. With the help of these two, it is getting converted into DC current. And see from here, from this dotted line to this dotted line, this is a DC line, right? This is traveling from the Ethiopian border to the Kenyan border. And when it enters into the Kenyan border, it goes into same elements which are present over here, and now you see the direction is reversed. It is pointed upward, it is pointed downward, right? So what will it do? It will convert that DC current back into AC current, right? And this is Kenyan side of a 400 kV bus. Now this AC will go into Kenyan side, right? So how does an HVDC work? It has got two stations. One will be at one side of the AC bus and the other station will be on the other side, right? AC will be converted into DC, then the transmission will happen over DC, and then on the other side again what will happen? DC will be converted into AC, and this AC will be given to the grid. So in this way the transmission happens. Now in HVDC we call it, this system is called a bipole system. Why is it bipole? We call it bipole system, like this, right? Why is it called bipole? This is pole 1, this is pole 2. There are two poles, pole 1 and pole 2, pole 1 and pole 2. So we call it bipole system, right? Now, what are the equipments we have? We look at this diagram, and these equipment, when we visit the yard, we will see them in practicality, right? How they are located. These are converter transformers. These are thyristor valves, right? These two are called smoothing reactors, right? These are DC filters, right? And these are AC filters. Fine. This is a common area which is called electrode line. This is called electrode line. That's it. And the same thing will be on this side also. Right? These are two similar stations. The one which is transmitting the power is called rectifier, AC into DC, and the one which is converting DC into AC, it is called inverter. So on this side you have rectifier and on this side you have inverter. Fine. A small fluctuations of voltages. So when I put a reactor in series, this ripples goes away. The output of the reactor is smooth DC. Right? So this reactor is not the reactor which you have seen in AC. This is totally different reactor. Yeah, no. I will show you. It's an air core reactor. I will show you over here. It's an air core reactor, and it's just a coil, a big coil. You will see it.
How about this issue, double circuit, single circuit? Do we have it in DC?
Double circuit, single circuit.
Yes.
Okay, wait. I will. We don't have double circuit or single circuit. Just a second. I have it over here. Whatever here, let's talk about this one. This is a slide which shows you mode of operation, right? Just a second, I take it out. Now, when you talk about single circuit and double circuit, in AC transmission, we have here different modes of operation. What we have is, this is called, first of all, bipolar mode of operation. See over here, this is working, all the red lines are working. This is working, right? This is called bipolar mode of operation. When both of the poles are working. Second is monopolar ground return. Let's suppose there is a fault on this pole and this pole, right? Then though power will flow from here to there or there to here over this line, but this will continue, the power will continue to flow in this network, right? This is called monopolar ground return. Here in DC you don't have phases, you do not have single circuit and double circuit. What we have is two lines. One line, this is positive. Second line, this is negative. These two lines will be there. Fine. Either both of the two lines will work or one of the two lines will work. But they will work. So there is no double circuit or single circuit. There are only two conductors. One is positive, other is negative. When this works in this of modes, where you have only one working here and one working here, right? And ground is acting as a return path. Do you understand this thing? In DC, the current should return to its source. If the current has started from here, it will go over here, but it should return back here. So in this case, the current path is from here to the DC line, and from the DC line, this is ground. From ground to back to this station. This is called monopolar ground return. Return path is from the ground, right? We have put electrodes in the ground. The current goes into the ground at one end, let's say in Zopier end, and it comes out from the Kenyan end. The it travels through ground. Then you have another way, monopolar metallic return. In what we do, we say okay, we do not want the current to flow from ground. What we use the other conductor. The current flow like this, like this, like this. Instead of going to ground, we cause him to go here, and the second DC line will act as a return path. This equipment. This is this equipment. These are thyristor valves. They are semi-conductor devices. They convert AC into DC. Now they are arranged in this fashion. Right? It's a. Have you heard about 6 pulse bridge, 12 pulse bridge? How many thyristors are here? How many thyristors are here in this diagram? Yes. Total thyristors. 12. It's called a 12 pulse bridge. Right? This is a standard bridge used all over the world, having 12 valves, thyristors. Right? This is called a single valve. This is called a double valve, and this is called a quadruple valve. They are arranged in this way. And next slide, I will show you its photo also, real photo. And these are the, you know what I meant? These are? No, these are the windings of the transformers. You see over here? It is connected to the transformers. So, pictorially, in picture, we have represented this as a valve winding, transformer windings, right? This is the actual thyristor valves, right? See, they are hanging from the. Yes. They are exactly similar. In the similar fashion, they are arranged in the valve from up to down, right? This is one valve. Then you take two. This is two valve. Then this whole structure is called quadruple, right? Like this, you have got 1, 2, and this 3. There are 3 different structures. You can see this is 1. These 2 are 1. Then again these 2. This is another one, and last 2 are another one. Similarly like this. See? 1, 1, and 1. Right? Now these thyristors are, first of all, they are suspended from the roof, right? And second, they are water-cooled. What does it mean by water-cooled? During transmission, conversion of AC into DC, they produce a lot of heat. A lot of heat is produced. So, to keep thyristors cool, we have a cooling circuits in which water is stored. and it takes all the heat out of the system, right? This is actually what a thyristor look like. This is one thyristor. It's a small disc type structure. Now I told you about the wall cooling, right? Now this is wall cooling system. How the water is flowed, right? So first of all, its purpose is to take the heat out of the converters. Second, it uses deionized water. It does not use the normal water. What does it mean? The cations and anions in the water is being removed because it is flowing inside the thyristors, and thyristors are conducting electricity. So if you flow a normal water which has a lot of ions inside it, the water will become conductive, right? So it uses deionized water, and its conductivity is always kept below 0.5 microsiemens per centimeter. Fine. And this is a closed loop cycle. What does it mean? That water will keep on running and it should not come out.
What did they use cements? Are they the ones who invented this?
Sorry?
What did they use cements? That's
Siemens. Yeah, this Siemens.
I'm saying why?
This is this is the unit of conductivity. Do not go by the
Sorry, I'm not an electrical engineer, so I'm a little different now.
No. It's not about that company Siemens.
No.
Both are coming on one. So the outgoing is yellow.
Yes, both are outgoing.
Okay, this is number one.
Now two. Yeah.
But that's
The station.
okay, we hear this safety in the substation where you don't
Step potential.
so many years.
Yeah.
Here, how does it? See? It should always keep also small steps.
Look this.
No problem.
No problem.
So I can even run through.
Yes. Why we run? First step potential, we have taken this small stones. These small stones. They are used to reduce the step potential. They are used to